Hello everyone. So we're going to be doing this question on of building a solenoid. So this question is basically in chapter 29 of Eric Mazur. So we're going to be doing this question. So they say you build a solenoid containing 400 turns or 400 windings. We know that 400 windings we denote it as N, which is 400 windings over a length, let's call this length of 0,025 meters. And they say for each windings, if the current in the unit it's 3 amps, let's see our current, that's saying it's 3 amps in our solenoid. So basically, for those who have no idea what is a solenoid it's a circular shape of windings of wires. It's like when you have a wire, then you rotate it, like you do it a coil like this is a solenoid. So they are saying it has 400 windings and it has current of 3 amperes. Okay, so they're saying what are the magnitude of the magnetic field. They want the magnitude of the magnetic field. So to find the magnitude of magnetic field, we need to use these formulas, because the magnetic field is defined as P of the permittivity, the number length per unit area, and also is defined as, I wanted to show you something here. This is the Eric Mazur textbook. So this is basically chapter 29 of charging of magnetic field. So to find that formula of magnetic field, you gotta check it here. So they gave us a proof of it. So let's find it. Magnetic field closed. This is inductance, magnetic energy. We're gonna come back here on magnetic energy for the next question. So let's find our magnetic field. So basically, if you go back into this textbook and you go to chapter 28, you will find the magnetic field defined as permittivity. This is a constant which is equivalent to 4 pi times 10 to the power minus 7, and therefore is number of turns per unit length, and also it has current in it. So this is the formula for magnetic field of a coil. So basically what we're gonna do right now, we're gonna substitute the number of windings per unit length in here. So we can call this equation 1, then we call this equation 2. Then we say substitute equation 2 in equation 1. So what I encourage you guys is to start by resolving the equations, and then you will substitute back in it. So let's find the magnetic field. Our magnetic field is gonna be, remember here I substituted this number of windings per unit length, therefore times current. So since we have all these variables, this is a constant, which is 4 pi times 10 to the power minus 7, and also we have the number of windings defined as 400 windings. We have the length of 0,025 meters. Don't worry about the units right now. We can just find our units after. Know our unit for magnetic field is Tesla. So we multiply by 3. So your answer will be 4 pi multiplied by 10 to the power minus 7. So we have 100.25. You can tell me in the comment whether you get this value of 0.06 Tesla. This is Tesla. It's the unit for magnetic field. So let's go back to another question. The next question says that calculate the inductance. Okay. So basically, to calculate the inductance, we need to know what is a inductance. We need to know what is a inductance. So inductance here is this one. So it's defined as how much change in magnetic field magnetic flux is associated with a change in current. So how much change in magnetic flux is associated with a change in current. So let's see how in this book they defined the magnetic flux. So they defined it with using this diagram. So we know that the induced EMF is directly proportional to the rate of change of magnetic flux and directly proportional to the electric field, directly proportional to the current. So we're going to use this relationship. So they're saying we can define inductance as L. They use this L of a loop of a solenoid as a constant of proportionality between EMF and the rate of change of current. So they defined our inductance as a constant. So we know that whenever we have the EMF, which is directly proportional to the rate of change of current, so we're gonna use our proportionality constant to make this formula nice. We define as the inductance. So that's how we define inductance. So the unit for inductance, it's Henry, which is equivalent to this 1 kilograms meter squared per cubic coulomb, per square cubic coulomb. So another relationship that we can use is the relationship of the rate of change of magnetic flux is equal to this is equivalent to the induced EMF, which is the change of magnetic flux, which is equal to the inductance. Basically is this formula. So we're gonna go back to that question and do it. So basically what I said is the inductance, it's how much change in the magnetic flux is associated with the change in current. So let's go back to this question. So we defined our inductance So if you go, our inductance as be the inductance is a proportionality constant, the rate of change of current, the rate of change of time. So let's go back to our formula, which is formula 29,8. Let's go back to formula 29,8. Where we're going to find the relationship between the solenoid and the inductance. 29,8, which is this formula. So we're gonna use the formula for inductance that has the variables that we are given here, the variables of N, which is the number of windings, length, and current, and resistance. So to find this, we're gonna have to use the inductance for a solenoid, right? So this is the general formula that we can define inductance. But in chapter 28, we have learned that inductance can also be defined as so it can be defined as the constant of permittivity, number of windings squared, and the area divided by the length. So basically, how did they derive this formula? They derived this formula from the magnetic field. So I'm going to take steps of how did they define this formula of the inductance. So step number 1, we have our magnetic field that we know as permittivity, number of windings per unit length, and the current. So now we're gonna substitute the number of windings per length. Number of windings per length is this, and also the current. So we have this formula. And also we need to go back again and realize another situation, another thing, which is this is magnetic field. So now I'm gonna use magnetic flux. So let's use magnetic flux. Magnetic flux is defined as the number of windings and also BA, which is the number of windings, the magnetic field, and the area. So let's go through it. So let's substitute our formula of magnetic field in here. So we're gonna substitute our magnetic field, which is NB. Our magnetic field, it's permittivity, number of windings, divided by the length, and also we have our current. So we have our area after that. So we need to again to find the relationship between the magnetic flux, magnetic flux and inductance. So we defined our magnetic flux as from this equation. Inductance, we defined it as the rate of change of magnetic field. So we said we want to find the relationship between the magnetic field and the inductance. So to find the relationship, we're gonna use this relationship. We use this relationship. So where the rate of change of the magnetic flux is equal to the permittivity times the rate of change of current. So let's go back to our formula where we said that the relationship is defined as the magnetic flux, the rate of change of magnetic flux equals to the permittivity and the rate of change of current. So let's substitute back this equation here of magnetic flux in here. So we're gonna substitute it as, okay, let me continue in another page. We're gonna substitute our magnetic flux, which is so let me simplify this equation. This equation is defined as the permittivity and also number of windings squared multiplied by the current area, all divided by the length. So we will substitute this formula, which is permittivity, number of windings squared, current, area, all divided by the length. We can say the rate of change. So remember, we are using this formula in here. So this is equal to the inductance, the rate of change of current. So this is the relationship that we have built. So basically here we are deriving the formula of inductance. So I want to go back again. where I said we need to find the magnetic field, which is defined as this in this formula. And also after finding the magnetic field, we need to find our magnetic flux. Step 2. Magnetic flux. From there we go, we find the relationship between the magnetic field and the inductance, which is defined with this formula. So again, let's continue with our derivations. So basically what is going to happen now, d t's, they're gonna cancel, and also here we're gonna be left with this formula, which is the one that I have defined it for you, which is this. After all the derivations, gonna be left with this formula of inductance as n squared I, therefore divided by the L, also inductance and our current. So basically now we are happy since we have this in here and this in here, the current. So they're gonna deal with each other, meaning that they're gonna cancel each other. So our formula for the inductance, it's gonna be L, which is our inductance, permittivity, number of windings squared, we have area divided by the length. So basically this is the derivation of the inductance, which is this formula. I'm sure now you know where it comes from. So let's answer this question now. They're saying we need to find the inductance in the solenoid. We have 400 windings. We have our length as 0.025 meters. We have our current as 3 amperes. So we have, this is the constant of permittivity, which is 4 pi times 10 to the power minus 7. We have 400 windings. So the area of the solenoid is defined. This is the area as pi r squared. So I'm gonna substitute it here as pi. Our radius, they give us the radius. Let's see if we have the radius. Yeah. So basically this is the radius. So our length, it's gonna be 0.20, which is this. If you can see it well, this is it. Saying we are building a solenoid containing 400 windings over 0.2 length. So our radius is gonna be 0.025 squared, and also our length is gonna be 0.2. So what you will find now, tell me if you find the correct answer, which is to which is inductance is 1,97 multiplied by 10 to the power minus 3 henries. So this Henry comes from here. They said inductance, the unit for inductance is Henry, or you can define it as kg, meter squared per squared coulombs. So let's move on to another question. Another question says that use the value of B in part A to calculate the amount of potential energy stored in the solenoid. Okay, now we are going to potential energy. So we know potential energy is UmgIh. So now we are talking about the electrical potential energy. This is potential energy due to gravity. Now we're talking about the electric potential energy. So the electric potential energy is defined as UB half of the permittivity and squared A and I squared. So I'm sure you're wondering, where does this formula come from? So I will peg it out. So we have our, so basically our derivations comes from here. We have our work defined as voltage and Q which is the charge. So now we use the EMF and the charge. This is the EMF induced, so we're gonna focus on the power source. So again, our work, it's going to our work, we need to find the small intimately small portions or small portion of work as induced dq. So in finding this, now we're gonna have to use the relationship that we have for the induced EMF, which is this. So we're gonna see W. So we divide by the dt everywhere. Our EMF is defined as okay, let me go back and do it in the slide. So let's define our potential energy. So we need to see where it comes from. Potential energy. So potential energy, we're gonna start with this relationship of work equal to, this is equation 1, work equal to Q. voltage and Q. So as I said, now we're gonna use the induced EMF. We need to find the small portion, which is the derivatives, dW and dQ. So after finding that, we're gonna divide everything by dt. Therefore, number 2, I'm going to use this which is equal to current. So our dW dt is equal to induced current. So our current is the rate of change of charges, the rate at which charges moves. So we defined our induced EMF, I think somewhere we defined it as our induced EMF as the L of di and dt. We defined our induced EMF as this. So now I'm gonna substitute this EMF in here. And I will have dW dt. So now these negatives will deal with each other. So I'll substitute this formula, then current. So now our dW is defined as inductance current, the derivative of current and time. Okay, so now we are happy. Remember, this is work. Sorry for writing the small w. This is work. So again, we know that work, let's remove these dt's now. Therefore our solution be nice. Our work is equal to inductance current and di. So we need to find work. In order to find work, we go back, we need to find the sum of all the works. So to do that, we're gonna use integration. We're gonna integrate both sides. After integrating both sides, now our work is going to be current squared divided by 2. Therefore, our work, which is equivalent to potential energy, is equal to half of permittivity I squared. This is the formula for the potential energy. So since from this statement we are given, we have number of windings, the radius, the length, and also the current, the length, and we calculated magnetic field as 0.06 Tesla, and also the magnetic flux, we calculated it, we got 1.97 times 10 to the power minus 3 Henry. This is the inductance, sorry. So now we're gonna find the potential energy, which is gonna be 1/2 the inductance. We got 1.97 times 10 to the power minus 3 Henry, which is this one. And also we have our current as 3 amperes squared. So I get the value of 8.87 times 10 to the power minus 3 joules. So thank you for watching till this far. Feel free to subscribe and put a like so that I keep on uploading more videos based on this section and this chapters. So make sure you comment wherever you have question, comment. I will fix it in the next video.